Are we chasing the wrong second Earth? Are we actually any closer to finding another Earth, or have we been projecting our hopes onto the wrong star system? For years, one name has carried more of that hope than almost any other: TRAPPIST-1. In the hunt for alien life, this tiny red dwarf has become almost mythic. You have probably seen the posters. 7 worlds, lined up like jewels, endless blue oceans, soft clouds, warm sunsets around a faint, ruby star. It feels like a promise. A whole miniature solar system of Earth-like planets, just 39 or 40 light-years away, waiting for us. But what if that promise is an illusion? What if those 7 ocean worlds are not lush and habitable at all, but mostly dead, airless rocks, baked and blasted by their star? What if our favorite candidate for a second Earth is, in reality, a mirage, created by wishful thinking, sparse data, and beautiful artist impressions? It should be noted that TRAPPIST-1 did not become famous by accident. For nearly a decade, this system has been the poster child of habitable exoplanets. Documentaries, science headlines, space agency animations. They all circled back to the same story. 7 rocky planets, all roughly Earth-sized, packed tightly around a cool red dwarf. At least 3 of them sitting in the so-called Goldilocks zone, where liquid water could exist. On paper, it sounded almost too good to be true, but while the posters showed calm seas and hazy blue skies, the physics was always harsher. This star is small and dim, so its habitable zone hugs extremely close in. This means every planet races around in a very tight orbit, likely locked with one face in permanent daylight and the other in endless night. And like many red dwarfs, TRAPPIST-1 bathes its planets in high-energy radiation that can strip away an atmosphere over billions of years. Optimistically speaking, that still leaves room for clever climates and hidden oceans. Pessimistically, it leaves behind bare rock. Until recently, we could not tell which picture was closer to reality. We had models, simulations, and a lot of educated guesses. Now, for the first time, we have something else. The James Webb Space Telescope has started to take direct measurements of these worlds, their temperatures, their atmospheres, or their lack of atmospheres, their response to the star's flares. So it's time to find out the truth. Are we looking at the most exciting roadmap to life beyond Earth, a system that will guide how we search the galaxy? Or is TRAPPIST-1 the most overhyped exoplanet system of the decade, a beautiful story that collapses under real data? So, let's begin. By the end of this video, you will be able to answer that yourself, with evidence, not just posters. From Cosmic Dream to Data Check, why TRAPPIST-1 matters so much to answer that, we have to zoom out for a moment. Do aliens exist? There are very few questions more profound when it comes to our place in the universe, in the hunt for alien life. We are really asking 2 things at once. Are we alone? And if not, how common are worlds that look anything like Earth? Every new rocky planet, every distant star system, is another tiny data point in that search. We know that Earth-like planets are fertile ground for life. After all, life arose here. So when astronomers announced, in 2017, a single red dwarf star, just 39 light-years away, with not 1, but 7 Earth-sized planets, at least 3 in the so-called Goldilocks zone, it felt like a science fiction dream suddenly made real. This was not just another exoplanet. This was a potential mini-solar system of habitable worlds. The story that followed was incredibly powerful. Headlines shouted about 7 Earth-sized planets and the most promising place to look for life. Space agencies released posters imagining vacations on TRAPPIST-1 or TRAPPIST-1/5. Animations showed deep blue oceans, white clouds, and sunsets over alien horizons. It should be noted that almost all of this was artwork, not measurement. But while the images were speculative, the emotional impact was very real. Why did this particular system capture us so strongly? Partly because it concentrated our hopes. Instead of hunting for a single lucky planet around a distant star, we suddenly had 7 targets in one compact system. If even one of them had a thick, protective atmosphere and liquid water, that would suggest habitable planets might be common. If several did, it would be revolutionary. But while the narrative was simple, the science was not. Detecting the atmosphere, temperature, and surface conditions of a small rocky planet across dozens of trillions of kilometers is extraordinarily hard. Before JWST, we relied on telescopes like Spitzer and Hubble, using indirect techniques and very noisy data. This means early models of TRAPPIST-1's planets were built on hints and assumptions, not clear detections. TRAPPIST-1, however, was just too tempting to ignore. The planets are tightly packed and all pass directly in front of their star from our point of view. They orbit quickly, some in just a few days, giving us many repeated chances to watch starlight filter through any atmosphere. And because the red dwarf itself is so small and dim, the relative signal from each planet is larger than usual. Optimistically speaking, it was the perfect laboratory for testing our theories of rocky, potentially habitable worlds. Combine that irresistible setup with limited data and a deep human desire for a second Earth, and hype was almost guaranteed. So it's time to find out the truth. Now that JWST is finally staring at this system, what survives contact with real measurements, and what quietly dissolves? To answer that, we need to look much more closely at the star and its 7 mysterious planets. And that is where the story becomes far more complicated than the posters ever suggested. Meet TRAPPIST-1, the tiny star with 7 Earth-sized worlds. So what is this system? Really? Once we strip away the posters and the headlines? To answer that, we have to meet the tiny star at the center of all this attention, TRAPPIST-1. TRAPPIST-1 is an ultra-cool red dwarf about 39 to 40 light-years away in the constellation Aquarius. In the vast scale of the Milky Way that is practically next door, this means its light reaches us in just a few decades, not thousands of years, and our telescopes can pick apart its planets in far more detail than most distant worlds. In the hunt for alien life, proximity is power. The star itself is only a bit larger than Jupiter in size, yet far more massive, and it glows a deep, cool red. Its Goldilocks zone, the region where temperatures could allow liquid water, hugs incredibly close to the star. All 7 known planets crowd into orbits smaller than Mercury's path around our sun. Some of them complete a full orbit in just a few days. It should be noted that this makes the system feel like a miniature, compressed version of a solar system, sped up and squeezed inward. Each of those 7 worlds is roughly Earth-sized and almost certainly rocky, not puffy gas giants. That alone was remarkable. Instead of one possibly Earth-like planet, astronomers suddenly had 7, lined up like beads. Even better, at least 3 of them, TRAPPIST-1, FG, fall within the traditional habitable zone, where, with the right atmosphere, liquid water could exist on the surface. On paper, it looked like a jackpot. Why was that configuration such a big deal? Because it turned TRAPPIST-1 into a natural laboratory. With one compact system, we could compare how planets with similar sizes but slightly different orbits respond to the same star. Does one keep a thick atmosphere while its neighbor is stripped bare? Does water survive closer in, or only on the outer edge of the habitable band? Optimistically speaking, this was the dream dataset for testing our ideas about how rocky planets form, evolve, and maybe become habitable. And there was a deeper promise, too. If even one of these worlds managed to hold on to a stable, thick atmosphere and surface water, it could become one of the best places in the nearby universe to search for biosignatures. So, let's begin to ask the uncomfortable question. When we finally point our most powerful space telescope at this supposedly perfect system, do we see blue skies and gentle oceans, or bare rock and harsh radiation? That is exactly what the James Webb Space Telescope was built to investigate. In the next section, we will see how JWST turns TRAPPIST-1 from a hopeful poster child into a hard test of what real data can tell us about alien worlds. Enter JWST, the cosmic lie detector, aimed at TRAPPIST-1. So, if TRAPPIST-1 is the poster child, what kind of camera do we need to see past the makeup and down to the bare skin of these worlds? To do that, we built the James Webb Space Telescope. JWST is, in many ways, the most powerful space observatory humanity has ever launched. Its 6.5-meter gold-coated mirror is like a giant light bucket, unfolding in deep space to collect photons that are billions of times fainter than what our eyes can see. But the real magic is that it works in infrared, tuned to faint heat signatures, and to starlight that has passed through the thin shell of a distant planet's atmosphere. This means JWST is not just taking pretty pictures, it is dissecting light. When a TRAPPIST-1 planet crosses in front of its tiny red dwarf star, a small fraction of the starlight filters through whatever atmosphere that planet has, if it has one at all. By measuring how the star's brightness changes at different wavelengths during these transits, we can infer which gases are present, or whether there is any substantial atmosphere in the first place. In the hunt for alien life, this is a game changer. Before JWST, we could do this kind of transmission spectroscopy mainly for big, puffy gas giants. Rocky, Earth-like planets were simply too small and too dim. TRAPPIST-1 changed that by packing 7 Earth-sized worlds in tight orbits, and JWST completes the picture by finally giving us the sensitivity to probe them. It should be noted that several of JWST's instruments are now effectively cross-examining this system. NIRSpec splits the starlight into a detailed spectrum during transits, searching for fingerprints of molecules like water vapor, carbon dioxide, or methane. NIRIS, a Canadian contribution, performs ultra-precise measurements of the same kind, providing an independent check And then there is MIRI, looking at longer wavelengths, which can directly measure the thermal glow from the day side of hot inner planets such as TRAPPIST-1b. Pattern interrupt. This is the first time in history we can realistically measure the heat leaking off the surface of a rocky exoplanet and say, is this world wrapped in air or naked in space? For years, we have had artist impressions of turquoise oceans and soft clouds around this star, but while the posters were beautiful, they were guesses. So it's time to find out the truth. JWST's first observations of TRAPPIST-1 are like putting the system under oath. No more idealized models, now the star and its planets have to testify through hard data. Optimistically speaking, JWST could reveal that at least some of these worlds sit in the Goldilocks zone, with protective atmospheres, warm surfaces, and maybe even stable liquid water. Or it could show us a harsher reality, bare rock, stripped air, and intense radiation from the red dwarf. In the next section, we will walk through that evidence, planet by planet, and see which version of TRAPPIST-1 survives contact with the universe. Paradise or dead rock? Framing the TRAPPIST-1 verdict. So, let's begin by sharpening the question we have been circling around. Are these 7 worlds a compact chain of potential oases, each with its own climate and maybe even oceans, or are they mostly dead, scorched, airless rocks locked face first to a volatile red dwarf star? There is very little middle ground here. The answer leans one way or the other. In the hunt for alien life, TRAPPIST-1 became the poster child for optimism. Those early artist impressions showed blue seas, clouds, and sunsets over multiple Earth-like horizons. It felt almost obvious that, with 3 planets in the classic Goldilocks zone and 7 Earth-sized worlds in one tight system, at least one had to be habitable. But while the images were beautiful, they were not photographs, they were guesses. Now JWST is replacing those guesses with data. This means we can imagine 2 very different stories unfolding as the observations accumulate. In the first story, JWST vindicates the early excitement. We find that a planet like TRAPPIST-1 holds on to a stable atmosphere, perhaps with temperate dayside temperatures and a nightside cold trap of ice, balanced by winds. Maybe we even detect hints of water vapor, or see thermal patterns that only make sense if there are clouds and an active climate. In that timeline, TRAPPIST-1 is not overhyped at all. It becomes the closest thing we have to a multi-planet laboratory of truly habitable worlds. In the second story, JWST slowly dismantles that dream, one planet at a time. We have already seen that the innermost planets, like TRAPPIST-1b, look bare and almost airless. Optimistically speaking, we could still hope the middle worlds are different. But what if the same pattern repeats? What if every measurement points to thin or absent atmospheres, extreme temperature contrasts, and surfaces blasted by high-energy radiation from the star? Then TRAPPIST-1 does not become less important. It becomes a warning about how hostile ultra-cool dwarf systems may be. It should be noted that this decision between oasis and graveyard is bigger than one star system. Red dwarfs are the most common stars in the Milky Way. If TRAPPIST-1 turns out to be friendly to life, it suggests the galaxy could be full of small, cool suns with Earth-like planets quietly thriving in close orbits. If it turns out to be hostile, then a huge fraction of potential homes for life suddenly look much less promising. So it's time to find out the truth behind our title. Is TRAPPIST-1 overhyped as a future home for life, or have we simply hyped it for the wrong reason, as if it were a guaranteed second Earth instead of what it might really be, a harsh but invaluable lab for testing how rocky planets behave under extreme conditions? Before we can judge the worlds, though, we have to face something more fundamental. We need to understand the star they orbit. And this is where the story takes a darker turn, because the very thing that makes TRAPPIST-1 so useful for astronomers may be exactly what makes it dangerous for life. Who's talking to you? Roadmap for cracking TRAPPIST-1. So if the star itself might be hostile, how do we even start judging whether this system is overhyped or misunderstood? We need a plan, because TRAPPIST-1 is one of those places where imagination has been racing ahead of the data. And our whole goal today is to give you enough context that you can read a JWST headline and actually know what it means. This episode is not about telling you what to think, it is about giving you the tools to decide for yourself. So, let's begin with the rules of the game. Before we talk about any specific planet, we have to understand how stars and planets work together to make a world habitable. What does it really mean to sit in the Goldilocks zone of a red dwarf? How do things like tidal locking, high-energy radiation, and long stellar lifetimes push a planet toward, or away from, being Earth-like? This means we will first build a simple checklist for habitability that we can apply over and over. Then we will zoom in on TRAPPIST-1 as a star. It should be noted that this ultra-cool red dwarf is not a generic example. It flares less often than many of its cousins, yet still bathes its planets in intense radiation over billions of years. We will compare it to a typical M dwarf, see why astronomers were were initially optimistic and why that optimism has now become more cautious. After that, we will rewind the story. Why did TRAPPIST-1 become the poster child for a mini solar system full of Earths? We will walk through the discovery of the 7 planets, the first hints of multiple worlds in tight orbit, and how artist impressions of ocean-covered spheres around a tiny star captured the public imagination. This is where we ask, in the hunt for alien life, did the narrative get ahead of reality? Only then do we let JWST speak. We will go planet by planet, from B all the way out to H, and look at what the telescope has actually seen so far. Atmospheres or no atmospheres. Temperature clues from thermal emission, how flares may have stripped some worlds bare while leaving others as possible refuges. So it's time to find out the truth about which ideas survived contact with real data and which did not. By the end, you should be able to answer 2 questions with confidence. Is TRAPPIST-1 overhyped as a home for life? And if so, what is this system actually good for scientifically? Optimistically speaking, it may be less a promised second Earth and more a harsh laboratory for rocky planets. One quick challenge for you. Right now, quietly pick a favorite planet. B, C, D, E, F, G, or H. Hold on to it. See if your choice survives the evidence we are about to unpack, or if the universe forces you to change your mind. The harsh rules of alien real estate. Habitability 101. So, let's begin with a blunt question. What does it actually take for a planet to be habitable, not just pretty in an artist's impression? In the hunt for alien life, habitability is not a single light switch we flip to yes or no. It is more like a stack of fragile filters. You need the right star, the right orbit, the right atmosphere, the right planetary history. Miss even one layer, and an Earth-sized world can end up as lifeless as Mercury or as suffocating as Venus. Same basic ingredients, very different outcomes. To make sense of TRAPPIST-1, we first have to separate what belongs to the star from what belongs to the planets. On the star's side, the rules start with energy. How bright is it? How much total power does it pour into its system, and at what distances? Then, there is the spectrum. Does it shine mostly in visible light, like our sun, or in the deep red and infrared, like a red dwarf? This matters because different wavelengths interact with atmospheres and surfaces in very different ways. It should be noted that stars also have personalities. Are they stable over billions of years, or do they flare violently, flooding nearby planets with X-rays and ultraviolet radiation? Do they bathe their system in a gentle, steady glow, or in bursts that can strip atmospheres away molecule by molecule? This high-energy environment sets the outer limits of what any planet can hope to keep. On the planetary side, the checklist is just as strict. A world's size and mass control its gravity, which in turn controls whether it can hold on to an atmosphere at all. Too small, and gas simply leaks to space. Add a magnetic field, and you gain a shield against charged particles from the star, lose it, and the upper atmosphere is exposed. Internal heat from radioactive elements and tidal flexing drives, volcanism, and plate motion. Recycling gases, and possibly stabilizing climate over long timescales. Without that inner engine, a planet can freeze or dry out permanently. This is where the famous habitable, or Goldilocks, zone comes in. It is not a promise of oceans, it is just the orbital range where, given a suitable atmosphere, liquid water could exist on the surface. This means there must be an atmosphere in the first place, and it must have survived the star's tantrums. A bare rock in the Goldilocks zone is still just a rock, so it's time to find out the truth about why astronomers start with the star. The star sets the boundary conditions, how much energy each planet gets, what kind of radiation it endures, and how rapidly any atmosphere is eroded. Change the star, and the entire game board of habitability shifts. And ultra-cool red dwarfs like TRAPPIST-1, they come with a cruel trade-off. They live for trillions of years, offering absurdly long windows for life to emerge. But while their light is gentle, their magnetic tempers are not. Especially in their youth, they can be hyperactive, flare-prone, and harsh. Optimistically speaking, that long lifetime is a gift. Realistically, the early radiation storm may be a curse. TRAPPIST-1 is both typical and unusual in this family, and in the next section, we will see why that contradiction is exactly what makes your chosen planet's fate so uncertain. Inside an ultra-cool red dwarf, why TRAPPIST-1's star is a problem. So if TRAPPIST-1's long lifetime is both a gift and a curse, what kind of star are we really dealing with here? To understand why this system is so controversial in the hunt for alien life, we have to step inside the physics of the star itself. TRAPPIST-1 is an ultra-cool red dwarf. with only about 9% of the Sun's mass and a diameter similar to Jupiter. But while its size is comparable to a gas giant planet, its density is far higher. This is a true star, fusing hydrogen in its core, just doing so in slow motion. It shines at roughly 1,000th the luminosity of the Sun. This means that to receive Earth-like warmth, a planet has to huddle extremely close in, deep inside a compressed Goldilocks zone. Because it is so dim, every one of the 7 Earth-sized planets in this system orbits far closer than Mercury does to our Sun. TRAPPIST-1b whips around in just 1.5 days, and even the outermost, TRAPPIST-1h, completes an orbit in about 18 days. From above, the whole system looks like a miniature clockwork version of our own, scaled down and squeezed inward. It should be noted that stars like this are not rare curiosities. Red dwarfs are the dominant citizens of the Milky Way, making up the majority of stars in our galaxy. They sip their fuel instead of gulping it, which lets them live for trillions of years, far outlasting the Sun. Early on, that incredible stability made them very attractive targets for habitable, Earth-like planets. If life can arise, it would have time not just to appear, but to evolve for eons. But while that sounds ideal, there is a serious downside. Young red dwarfs are magnetically active and volatile. They unleash frequent stellar flares and blasts of X-ray and ultraviolet radiation. Now imagine a planet parked only a few million kilometers away. Over hundreds of millions to billions of years, that high-energy radiation can strip away an atmosphere, molecule by molecule, until a once-blue world is left bare. There is another complication. At such close distances, tidal forces from the star are intense, and the planets are expected to be tidally locked. One hemisphere bakes in permanent day, the other freezes in endless night. Could an atmosphere, if it survives, move heat around fast enough to prevent the dark side from seizing all the air and collapsing it as ice? Or does habitability exist only in a narrow twilight ring between fire and ice? Put together, this looks like a rough neighborhood for life. Intense flares, atmospheric erosion, tidal locking, and a Goldilocks zone pressed right up against a restless star. So, why did TRAPPIST-1 become our poster child for habitable worlds anyway? And is there something about this particular star that might soften the blow? So, it's time to find out the truth, and the answer is not what those early artist impressions led us to expect. TRAPPIST-1's saving graces, why astronomers didn't give up so if red dwarfs are such dangerous neighbors. Why did astronomers pin so many hopes on this one tiny star? Because TRAPPIST-1 is not a typical cosmic troublemaker. It should be noted that not all red dwarfs are equally hostile. Some are young, hyperactive, flare machines. Others, after billions of years, calm down. TRAPPIST-1 appears to fall into that second category. From its mass, brightness, and rotation, we think this star is ancient, possibly older than our Sun. And older red dwarfs usually mean fewer, weaker tantrums. Observations back this up. TRAPPIST-1 does flare, but when we compare its outbursts to the worst offenders in its class, the difference is dramatic. Studies suggest its typical flares are tens of times less energetic than those from more violent red dwarfs. This means fewer blasts of high-energy radiation slamming into the planets, and fewer chances to strip an atmosphere down to bare rock. Why does that matter in the hunt for alien life? Because atmosphere survival is everything. A planet can sit in the Goldilocks zone and still be dead if its air is gone. Around a quieter star like TRAPPIST-1, if these worlds started with thick atmospheres, especially heavier ones, dominated by molecules like nitrogen and carbon dioxide rather than fluffy hydrogen, there is at least a fighting chance that some of that air has survived. Not forever, and not perfectly, but long enough for interesting chemistry. Optimistically speaking, the middle of the system is where this hope really lives. Planets like TRAPPIST-1d, E, and F receive neither the brutal heating of the inner orbits nor the deep freeze of the outer ones. In that region, a relatively gentle but steady star, plus a dense, heavy atmosphere, could keep surfaces temperate for billions of years. That is exactly the kind of environment we look for when we talk about Earth-like conditions. And there is another twist. Because TRAPPIST-1 is so small and cool, its habitable zone hugs tightly around it. The planets pass directly in front of the star from our point of view, blocking a surprisingly large fraction of its light. This made their transits deep, obvious, and measurable, even with modest telescopes. Without that geometry, we might never have known this 7-planet system existed. JWST takes that advantage and pushes it further. A tiny star plus Earth-sized planets means the signal from any atmosphere, if it exists, is much easier to detect than around a sun-like star. In the hunt for alien life, TRAPPIST-1 is practically a custom-built laboratory. So this combination, many rocky planets, some in the habitable zone, wrapped around a relatively quiet, ultra-cool dwarf, looked like the best-case scenario in a difficult family of stars. TRAPPIST-1 was never our sun's twin, but it was the most promising red dwarf system we had. Astronomers knew lush blue oceans were a long shot, yet if any red dwarf system could surprise us, it would be this one. So, let's begin to understand how the hype really started by rewinding to the moment 7 hidden worlds suddenly appeared around this faint, unassuming star. How 7 worlds stole the spotlight, the TRAPPIST-1 discovery story. When did this faint red dwarf turn from an obscure catalog entry into the most famous exoplanet system in the world? To answer that, we have to start not with a giant space observatory, but with a pair of small, stubborn telescopes on Earth. The TRAPPIST project sounds grand, but in reality, it was 2 relatively modest robotic telescopes, one in Chile and one in Morocco, staring night after night at ultra-cool dwarf stars. Their mission was simple in principle, yet incredibly demanding in practice. Use transit photometry to watch for tiny, periodic dips in starlight as a planet crosses the face of its star. In the hunt for alien life, these little drops in brightness are our first fingerprints of distant worlds. So, what does that actually look like? Imagine the star as a perfectly steady light bulb. When a planet passes in front, the bulb briefly dims by less than 1%. By measuring exactly how deep that dip is, astronomers infer the size of the planet. By timing how often the dip repeats, they get the orbital period, and from that, the distance to the star and the amount of energy the planet receives. This means a simple brightness curve can reveal an entire miniature architecture of a planetary system. In 2016, that curve around one ultra-cool dwarf now called TRAPPIST-1 revealed something remarkable. 3 transiting, roughly Earth-sized planets. All of them around a single tiny star only about the size of Jupiter. It should be noted that finding even one such planet around such a faint object was ambitious. 3 instantly made headlines, but the story did not stop there. With more intensive monitoring from TRAPPIST, plus infrared eyes from NASA's Spitzer Space Telescope, and follow-up from larger ground-based observatories, subtle, extra dips and timing shifts began to appear. The planets were tugging on each other gravitationally, slightly altering their orbits. By early 2017, the puzzle snapped into focus. Not 3 worlds, but 7, all Earth-sized, all transiting. Transit timing variations allowed astronomers to estimate their masses, and when combined with their sizes, the densities came out consistent with rocky compositions. Here is where the hype ignited. 7 roughly Earth-sized, rocky planets, packed closer to their star than Mercury is to the Sun, with at least 3 in or near the classic Goldilocks zone. Artist impressions exploded across the internet. Ocean worlds with red sunsets, chains of planets hanging huge in each other's skies, even tourism posters inviting you to visit TRAPPIST-1e. Optimistically speaking, the public story became 7 Earth-like planets almost overnight, but while models painted temperate seas and thick protective atmospheres, the reality was that we had almost no direct information about those atmospheres at all. Were these worlds truly habitable, or bare, irradiated rock? So, it's time to find out the truth by looking at what newer, far more powerful observations have actually revealed, and what they have quietly taken off the table. Habitable zone versus habitable reality, where TRAPPIST-1 stands now. So, if the glossy posters and early headlines were a little ahead of the evidence, where are we actually now with TRAPPIST-1? In the hunt for alien life, that is the real question, with 7 rocky planets, at least 3 in the Goldilocks zone, circling a small but long-lived red dwarf. How many of these worlds could realistically be habitable today? To answer that, we need to zoom out and look at the system as a whole. TRAPPIST-1 is like a miniaturized version of our inner solar system, squeezed inward. Every single one of its 7 planetary orbits would fit comfortably inside Mercury's path around our Sun. The innermost planet, TRAPPIST-1b, races around the star in just over a day. The outermost, TRAPPIST-1h, takes only about 18 or 19 days to complete a full orbit. Imagine our entire inner solar system compressed so tightly that a year is shorter than a long vacation. This means the planets are close to their star and close to each other. Their mutual gravity tugs them into resonant rhythms, and tidal forces likely keep them tidally locked, with one side in permanent day and the other in endless night. It should be noted that this compact, synchronized arrangement is exactly why TRAPPIST-1 is such a powerful laboratory for rocky worlds, but also why habitability is so fragile here. So what has JWST actually told us so far? For the inner planets, especially TRAPPIST-1b and TRAPPIST-1c, the news is sobering. Transmission spectra show no sign of thick, puffy, hydrogen-rich atmospheres like mini Neptunes, and thermal measurements of TRAPPIST-1b reveal a dayside temperature pattern that matches a bare rock, or at most, a very thin atmosphere that cannot move heat efficiently. If we were hoping for cloudy, Earth-like skies on these inner worlds, the data are pushing us firmly away from that picture. Here is the pattern interrupt. Despite years of gorgeous ocean world illustrations, we still do not know for sure whether any TRAPPIST-1 planet has an atmosphere at all. JWST has only observed a subset of the planets in detail so far, and even then, we are mostly setting upper limits on what kinds of atmospheres they do not have. We can say, not a thick hydrogen envelope, or not a Venus-like CO blanket of a certain pressure, long before we can confidently say, this one is truly Earth-like. Optimistically speaking, that uncertainty cuts both ways. A lack of evidence for an atmosphere is not yet evidence of absence, especially for the mid and outer planets. But while we wait for more data, we have to be honest, everything we are about to say is as of now and could be sharpened or overturned by future observations. So, let's begin the detailed tour. In the next segment, we will go planet by planet, from B all the way out to H, and give each world a rapid profile, its orbit, size, gravity, what we expected its atmosphere to be like, and what JWST has actually seen. Keep your earlier favorite planet in mind, and see if it survives contact with the evidence. Planet by planet, JWST's verdict, and the truth about the hype, so it's time to find out the truth. We promised a planet-by-planet verdict, so let's begin at the hot end and move outwards, building the pattern as we go. TRAPPIST-1b races around its red dwarf in just about 1.5 days. It is almost Earth-sized, with similar gravity, and early on, many imagined a thick, steamy atmosphere. But JWST's thermal data show a huge day-night temperature contrast and no sign of a deep blanket of gas. This means B is almost certainly a bare rock, scorched and airless, not a habitable world in any realistic sense. TRAPPIST-1c follows on a 2.4-day orbit, again very close, again roughly Earth-like in size. Initial models allowed for a dense CO atmosphere, maybe even a mini-Venus. Instead, transmission spectra reveal no thick envelope, and its heat pattern also points to a stripped or extremely thin atmosphere. 2 planets in, the pattern is clear close to this star. Atmospheres struggle to survive. TRAPPIST-1d, on a roughly 4-day orbit, sits near the inner edge of the Goldilocks zone. It should be noted that its size and gravity are still compatible with an Earth-like surface, and early hype painted it as a warm ocean planet. JWST has not yet detected clear signatures of water vapor, CO, or methane, but it has ruled out a giant, hydrogenic shroud. If D has an atmosphere, it is likely compact and complex, and we simply do not know yet how friendly it is to life. Then we arrive at TRAPPIST-1e, the poster child. Its orbital period of around 6 days puts it in the middle of the habitable zone, with gravity and size extremely close to Earth. JWST has already excluded a puffy primordial atmosphere and a Venus-style CO blanket. In the hunt for alien life that is exciting, E could still host a thinner, Earth-like atmosphere, but at present we only have upper limits, not a detection. Optimistically speaking, this is still the best candidate in the system. Further out, F and G, with orbits of about 9 and 12 days, receive less stellar energy. They may have been better shielded from atmospheric erosion, yet they risk being too cold, with volatiles frozen out at the surface. TRAPPIST-1h, circling in roughly 18 days, is smaller, colder, and on the edge of what we can probe. Here, current data are sparse, and JWST's future observations will decide whether these outer planets carry substantial atmospheres or are simply icy relics. So, is TRAPPIST-1 overhyped? It was oversold as 7 Earths and a guaranteed refuge for life. JWST's early verdict is sobering for the inner worlds, but the system is not a disappointment. Instead, it is an unprecedented laboratory for understanding how rocky planets and their atmospheres cope around the most common stars in the universe. So, let's begin thinking about TRAPPIST-1 in a new way, not as a failed promised land, but as a crucial reality check that will guide where we look next. If you want to follow every new JWST data release on this system, make sure you subscribe, and tell us in the comments, which TRAPPIST-1 planet do you think still has the best shot at an atmosphere, and is this system overhyped or just misunderstood?